Let's look at question 3 from the 2025 free response. The answer key is not posted yet, so again, just take this with a grain of salt and check your answers with the College Board when they're released. This is just my perspective on this question. In 3A, I have to complete the Lewis dot diagram for P4. By drawing the non-bonding electrons, I can see that the bonding pairs are shown to me. So I like to use valence electron bank to solve questions like this. Phosphorus has 5 valence electrons. There's 4 of them in the molecule. So I've got 20 valence electrons total that I have to empty to 0. So remember that each bond, this that I'm highlighting, is 2 electrons. So 2, 4, 6, 8, 10, 12. We can subtract 12 valence electrons because they're occupied in bonds. That leaves me with 8 valence electrons. So I'm going to put the rest of my valence electrons as non-bonding lone pairs on each phosphorus. So 2, 4, 6, 8. That will empty my valence electron bank to 0. This is the correct answer. That will also give each phosphorus a stable octet. Moving on to question B, this one is about entropy and favorability. So the first part, I have to explain why is delta S negative for this reaction using particle level reasoning. So entropy is negative here because I can see that the reaction is getting more organized. So I'm going from 5 disorganized gas reactants or molecules. So 5 of these disorganized gas reactants formed one organized solid product. And so that's basically what this means. When delta S is negative, my reaction gets more organized or more orderly. If delta S was positive, then the reaction would get more disorderly. So because of how the equation is shown, this verifies that delta S, in this case, it does make sense that it's negative because the entire thing is getting more orderly. Okay, what about the next part? The enthalpy change of the reaction, delta H, is negative. And what I have to basically verify is, would the favorability of the reaction be driven by the enthalpy, not entropy? So that is true because we know that a reaction is favorable when delta H is negative, so when it's exothermic, as opposed to being endothermic, because you'd have to absorb a lot of heat if you were endothermic. So when delta H is negative and when delta S is positive, these two things will drive the reaction forward and make delta G negative. Delta G, by the way, equals delta H minus T delta S. And so if I read my scenario in question 2, I see that the delta H was negative, so that's a good thing. Delta S was also negative because that's what it told me in part 1. So if the reaction was completed, I know that is not because of the entropy in this case. It must have been the enthalpy, which would have driven delta G to be a negative number. So that's basically the reasoning that since delta S is negative, entropy didn't drive the reaction. It's the enthalpy component that did that, okay? It's the delta H exothermic that allowed the reaction to be spontaneous. Okay, now temperature could also be a factor, but it tells me it's at 298 Kelvin, so that's a constant. So I think that this is probably the best way to approach that one. Again, the wording, my wording is not the best, so check the answers later when they're released. Okay, and the next question is a calorimeter problem. So I'm shown a diagram, I'm shown a chemical equation, and I'm given a lot of data down here. So first part, calculate Q released during the experiment. Okay, so Q is heat, and Q is usually the surroundings, so I'm going to label it Q sur. That equals MC delta T. So Q sur equals, okay, the mass. We just have to be careful because the surrounding is technically the water, but the P4O10, when you put that in the water, that becomes part of the solution. And in the question, it says that we're going to also use the specific heat of the solution. So that means I need to add up the two things to give me a mass value of 100.1 grams. The specific heat capacity C is, again, I'm going to use of the water. So 4.18 joules per gram degree Celsius. And then the temperature, delta T, is final minus initial. So that would be positive 0.38 degrees Celsius. So mathematically, Celsius and grams will cancel out. And that will give me my answer in joules, and I'll get 160 as my answer. We do have to convert it to kilojoules. So I'm going to take my decimal and move it 1, 2, 3 to the left. That equals 0.16 kilojoules. So this is my answer for part C1. Okay, now let me get rid of some of this. Okay, for part C2, we have to calculate enthalpy. Delta H of reaction. So there's a formula that will equal Q of reaction over moles. So Q of reaction, excuse me. So Q of reaction is going to be negative Q of surrounding, because if the surrounding gains this much energy, this is the law of conservation of energy. If the surrounding gains this much, then the reaction has to lose that much. So the Q of the reaction is negative 0.16 kilojoules. And then we also have to figure out how many moles of the reactant I have. That's the P4O10. So let me do that over here. Moles of P4O10 equals its mass, 0.100 grams, divided by its molar mass, which is given to me in the question, 283.9 grams per mole. Grams will cancel out. That will give me a mole value of 3.522 times 10 to the negative 4 moles. Okay, now that I have Q of reaction in moles, let's plug it into our enthalpy formula. So delta H Rxn equals negative 0.16 kilojoules divided by 3.522 times 10 to the negative 4 moles. This will equal, we have to be careful, we have to put the sign. So the answer is negative, it's exothermic. It's negative 454. Sorry, let me fix that. Negative 454 kilojoules per mole. Okay, that's how we do this question in question 3. Let's move on to D. This is a long question, right? Lots of components. Okay, question D. So what if you did this calorimetry experiment and you weighed out the 0.100 grams of P4O10 and the 100 grams of water? But in your second trial, some of the solid got stuck to the weighing paper and it was not transferred to the calorimeter or the water. So given that P4O10 is the limiting reactant, would delta T for the second trial be greater than, less than, or equal to the first trial? Less than, because you didn't finish the reaction. Because, for example, if 0.100 grams gives you a temperature change of 0.38 degrees Celsius, if you, let's say, only scraped in, 0.5 grams, then your temperature change is going to be half of that. So, so we're going to have less than because you did not use all of the reactant in the water. Okay, the next question in E, I have to find delta H down here using Hess's law. So I'm going to find delta H by adding up equations 3 and 4 and then adding up their delta H's as well. Now, before I add them up, I need to make sure I make the equations the same as equation 5. So for example, I have 1/4 P4 in equation 5, but I have 1 mole of P4 in equation 3. So I'm going to multiply equation 3 by 1/4. Okay, because I want this to match. So that means I'll have 1/4 P4, 6 times 1/4 is 3/2, so that gives me 3/2 Cl2, and then 4 times 1/4 is 1. Okay, now because I multiplied the coefficients by 1/4, I have to do the same thing with delta H1. And then in equation 4, I'm going to leave it the same because when I add these up, it'll give me my fifth equation. So by the way, PCl3, it's a product in equation 3 and a reactant in equation 4, so it will cancel out. And when you add up the rest, I will get 1/4 P4, 3/2 plus 1 chlorine will give me 5/2 chlorine, and then 1 PCl5, that's my product. So I don't have to change, by the way, this delta H. So if you add these up, I will get negative 375 kilojoules per mole. Okay, that's how we do this Hess's law problem or standard enthalpy problem. Okay, the final part of the question, I'm shown a diagram, and first part, I have to calculate Kp. So what is the value of Kp? That's my gas equilibrium pressure constant. And Kp equals the pressure of your products, so PCl5, divided by the pressure of your reactants raised to their mole ratio, but they're all 1-to-1 ratio here. Okay, just be careful because although this is a 1 liter container, it tells me that, each each gas has a pressure of 1 atmosphere. So if I look at the PCl5, I have 1, 2, 3, 4. There's 4 PCl5s there. So the total pressure of PCl5 will be 4 atmospheres. And then if you do the same thing and count up your reactants, I've got 2 PCl3s, so that'll be 2 atmospheres. And then I've got 6 chlorine, so 6 atmospheres. So if you do the math, K will equal 0.33, and this will be unitless, 0.333. Okay, and then does the Kp increase, decrease, or remain the same if the temperature was raised to 596 Kelvin from 546 Kelvin? Well, I see that this reaction is exothermic, so I can tell because the delta H is negative. So I'm just going to say this is plus 88 kilojoules here on the product side. That's what exothermic means, that the heat is a product. So if I increase the temperature, then according to Le Chatelier's principle, PCl5 will have more energy that it can combine with or absorb with, and that is going to shift my equilibrium to the left. So the equilibrium will shift left, causing the reactants to increase in pressure. So if I go to my K expression, my denominator will go up, and my numerator, the PCl5, will decrease because it is getting consumed by the extra heat, okay, because it's shifting to the left. So that will cause K to be smaller. So K decreases because the reaction shifts left, causing an increased pressure of your reactants. Now, mathematically, what that will do is that will give you a greater denominator, so that increases the denominator, and therefore it will decrease K. Okay, now you should probably also say something here. The reason the reaction shifts left, it's because it's exothermic. So according to Le Chatelier's principle, the product will consume heat, shifting it to the left. All right, this was a long video solution, but I hope that helps you with question 3. Thanks so much for watching. Leave any questions you have in the comment section. Thank you.